Well, hello everyone, and welcome to lecture 3 in this inorganic chemistry series, part of the chemical science SE5014 module. Again, we shift right across the periodic table today, and we jump the D block because we've considered the D block in some detail last year, and we focus or center our discussion around group 13. That is boron, aluminium, gallium, indium, thallium, and nionium. Now, this is the group of the periodic table where we divide the metals and non-metals. So there are a very wide variation in properties as you go down the group. Boron is a non-metal. Aluminium is a metal, but in certain situations behaves like boron and exhibits properties that are similar to non-metals in some cases. But widely, the last 4 elements in the group behave as metals. And we'll see how boron doesn't behave as a metal as we progress through the lecture. And I'm going to focus a lot of today's discussion on the chemistry of boron. Just a slight caveat that nionium is an artificial element. It was verified by the UPAC, the institution that verifies all things chemical, in 2015. Its name was confirmed in 2016, and it's an example of a super heavy element. So these are elements that have an atomic number of 113 to 118. They make up the very last row of the P block, and they've only ever been made in very, very small amounts, and we know next to nothing about their chemistry. Of course, we assume that the chemistry of the bottom member of this group will behave in a similar way to perhaps indium and thallium, but we simply don't have enough of it to be able to confirm that. So generally, we omit the element from our discussions. In terms of occurrence, then you can see the relative abundances of the group 13 elements on the graph at the top left of the slide here. You'll note that aluminium is relatively far more abundant than the rest of the group, and indeed it's the most abundant metal in the Earth's crust. So it occurs in aluminosilicates like clays and micas. The main sources of boron come as borax and kernite, and you can find these sources in the Mojave Desert in California. Gallium occurs with aluminium in an aluminium ore called bauxite. Indium and thallium then occur in very small amounts relative to the rest of the group as sulfides in various mineral ores. In terms of commercial importance then, aluminium is very commercially important, and when you compare it to the rest of the group, it's far more commercially important. Perhaps members of the later group are becoming increasingly more important as we find uses for things like indium and gallium in smartphone and flat screen television technology. But in terms of use, aluminium is by far the most commercially important. And if you were to tally up the uses of all the elements in the periodic table, then you'd find that aluminium is one of the most widely used metals in the periodic table, and it's second only to iron, of course, iron being very heavily used in steel. It's extracted via a process called the Bayer process, and you take the crude bauxite ore, which is primarily composed of aluminium oxide, but is found with all sorts of other impurities such as iron oxide, silicon oxide, and titanium oxide. They add this crude ore to a digester where it's mixed with a very concentrated solution of sodium hydroxide under pressure, which causes all of those impurity oxides to separate. They then treat that mixture with a stream of carbon dioxide, which precipitates aluminium hydroxide. You can calcine, so you can heat to very high temperatures then the aluminium hydroxide. That drives off water, and you are left with alumina, Al2O3. You can then separate the alumina, you can separate the aluminium from alumina via an electrolytic process in which you get aluminium at the cathode and oxygen at the anode. So the oxygen just bubbles away, leaving behind pure molten aluminium. So it's quite a lengthy process. It's quite an expensive process, but that's how we separate aluminium or extract aluminium. Boron, I'll go around this this diagram here in an anti-clockwise fashion. So I'll start with boron. The boron is extracted from its ore borax, and you first convert it to boric acid and then to the oxide. Indium tends to occur in minerals such as zinc sulfide, and when they extract zinc from these ores, you also get indium as a byproduct. Interestingly, thallium isn't really used that much anymore. We'll see why later on. It's actually a very toxic metal. It was used quite heavily in rat poison, but you can obtain it again by trying to extract other ores, other metal ores, or other metals from their ores, and obtaining things like thallium as a byproduct. Similarly, gallium is obtained from bauxite as the byproduct of the bioprocess that we saw on the previous slide. So you get it in there as something like gallium oxide. There's been a very large increase in the world production of gallium, owing to the increase in the use of things like gallium arsenide and gallium nitride in components for electronic equipment. So you can see I write there that 4G smartphones use 10 times more gallium arsenide in their electronic components than standard mobile phones. So there's been a massive increase in the use of gallium over the last sort of 10 to 20 years. In terms of uses, boron tends to be used in its oxidized form. You can see some examples of the two most commercially important borates there. So some kind of boron oxide anion, which is coupled with a counter ion. Borax and kernite being the commercial names for these things. Uses, it's overwhelmingly used in glass actually, and it has a very borosilicate glass has a very high refractive index and is used in optical lenses for things like microscopes. Borax has been used in pottery for centuries and still is used widely in the ceramics industry. And those borates, borax and kernite, make very good flame retardants. Aluminium then is used, as I said, very, very heavily. It's the second most commercially exploited element in the periodic table. It's used in transport. The Coke that you have at lunchtime will be packaged in an aluminium can. It's used heavily in construction, where it's alloyed with things like copper and magnesium to increase strength. And indeed, there is a form of aluminium oxide known as corundum or alpha aluminium, which is used as an abrasive. And this compound is the second most hard naturally occurring mineral. So it's second only to diamond, hence why it's used in abrasive materials. Gallium and indium, then, they're phosphides, arsenides, and antimonides, have very important applications in the semiconductor industry. They're used as transistor materials in LED displays. And you can see there has been quite a dramatic increase, particularly in the use of gallium over the past 20 years, and that's primarily as we shift towards smartphones and LED displays and that kind of thing. Thallium then doesn't have the same kind of use that the rest of the group does. It's has been shown to be efficient in some high temperature superconductors. So these are superconductors that can operate at a relatively high temperature. It's used, the 201 isotope is used in cardiovascular imaging. But overall production and world use has fallen because of its inherent toxicity. So it was used as an insect and rodent poison in the form of thallium sulfate, but it's just too toxic. It's dangerous to have these kinds of compounds around humans, particularly around small children, because relatively small amounts can be toxic and sometimes fatal to small children. Okay, so as I said, I want to spend the majority of this session looking at boron chemistry and a class of compounds, or two classes of compounds, that boron forms, known as the borane and carboborane clusters. And these have had quite an intense amount of research over the last few decades since they were discovered by a guy called Alfred Stock. They are defined as electron deficient clusters containing boron. So Alfred Stock, in the early 1900s, revealed that boron formed a range of hydrides of varying nuclearities, and we call these boranes. So they're just boron and hydrogen. And since these early studies, there have been a very large number of compounds that have been formed, both neutral and anionic. And there's now quite an intense amount of research that goes into boron chemistry and some potential uses in the biomedical industry. I show you there the structures of three relatively small boranes. You'll notice they're all kind of cage-like structures. Some are neutral, some are anions, and they all have varying numbers of boron and hydrogen. Now, we class the boranes, or we group the boranes, these borane clusters, into classes. So you can see there that there are 5 classes of boranes: a closo cluster, which is just a closed deltahedral cage; a nido cluster, which is an open cage derived from that closed deltahedron above; an arachnocluster, which is again an open caged structure derived from the first closed deltahedron, but this time with 2 vertices unoccupied; a hyphocluster, which hasn't been very well exemplified in research, quite difficult to synthesize; and a conjuncto cluster, which is where we have 2 or more cages which are connected together through a shared atom. We can think about the derivation of these nido and arachno structures as the parent deltahedral cage with a vertex removed. So you can see there the closer structure on the left, B6H62-, is a closed deltahedral cage. It looks a little bit like an octahedron. And if we remove one vertex from that, we are left with the nido class. So there's the B5H9. And if we remove another vertex or vertices from that, then we are left with the arachno structure. A small note on nomenclature. I'm not going to ask you to name these things in coursework or any exam. I just want you to have an awareness so that when you look at these things in the literature, you can identify or have an idea of their structure. The class of the cluster is stated as a prefix in italics. So here is the name for B4H10. You can see that it's that arachno cluster. The number of boron atoms is given by a Greek prefix. So here there are 4 boron atoms, and we give the Greek prefix tetra. Now, just like any nomenclature in chemistry, there are these ridiculous exceptions. And if there are 9 or 11 boron atoms, then we use the Latin prefix nona and undecca. The number of hydrogen atoms then are very simply given as Arabic numerals in parentheses at the end of the name. That follows for a neutral borane cluster. But of course, in chemistry, nomenclature can become quite complicated, and the rules are different if we have an anionic borane cluster. So I'd show you here the name for B6H62-. Again, the class of the cluster is stated as a prefix in italics, so you know that this is a closed deltahedral cage, so the cluster is closo. The number of hydrogen atoms now are given in the Greek prefix, and the number of boron atoms again given as a Greek prefix, again with the exception of 9 and 11 boron atoms where we use the Latin prefix. And we change borane to borate here to denote the fact that this is an anion. And we put the charge of the anion at the end as the Arabic numeral in parentheses with the negative sign to denote again that this is an anion. Crazy nomenclature rules. Now, this B6H62- structure has essentially we say a closed deltahedral cage or a closed octahedral B6 cage. So it's a closo structure because it's a closed cage. The blue spheres here are boron atoms. The white spheres are hydrogen atoms. Here each boron atom is connected to 4 other boron atoms within the cage and to 1 terminal hydrogen atom. And we can think of this, as I said a couple of slides ago, as a parent cage, right? So if we remove a vertex from that parent deltahedral cage, then we end up with a nido structure. If we remove 2 vertices, we end up with an arachno structure. Now, if I show you B5H9, which is a nido structure, we can see that it's related to that B6H62- structure I showed you on the previous page by a very simple removal of 1 vertex, right? It consists of a square-based pyramidal cage of boron atoms, each of which has a terminal hydrogen atom, and those 4 atoms that sit on the base of the pyramid there each have a hydrogen atom which bridges 2 of the hydrogens. So all that we've done to create, theoretically to create this nido structure is to take the parent deltahedral cage, remove a vertex, and then add a bridging hydrogen at the base of each at the base of the cage. Again, you can see then how the structure of B4H10, which is an arachno structure, is related to that first B6H62- by this time removing 2 vertices. So this structure has a far more open framework, and you can see that it's got 2 edge-sharing B3 triangles. And we'll see how this, you'll see when we come to predict the structures of these things, how this kind of impacts. So there are a large number of what we call parent cages from which nido and arachno cages can be derived. So you see here that we define a parent cage by the number of vertices, right? These are all closed parent cages. So a good example is when there are 6 vertices in the case of an octahedron, and therefore the parent cage is an octahedron. If there are 8 vertices, then the parent cage is a dodecahedron. This has important ramifications when we're trying to predict the structure of a borane based on its formula. And we'll see a couple of examples of this in a moment. Now, the problem is when you look at the chemistry of these systems, they're quite complex. And that complexity means that we can't use a localized bonding model. We can't use simple bonding models. So I can't use the SEPR theory to predict the shapes of these boranes, because when you look at them, the electron count doesn't add up, right? We can't just count off the number of bonds and count off the number of valence electrons and get a satisfactory picture of bonding in these borane clusters. i.e., the SEPR theory can't be used because the bonding is a little bit more complicated than that. What you have to do is invoke molecular orbital theory to explain the bonding in these systems. Now, you'll be very happy to know that I'm not going to ask you to consider molecular orbital theory for these systems, because there is a far simpler empirical set of rules which were developed by a guy called Ken Wade at Durham. And what these rules allow us to do is to calculate the parent deltahedral cage and predict the structure of the borane from its molecular formula. So think back to the last slide where I showed you all of those parent deltahedral cages. We can use those to predict the structure of a borane based on a relatively simple set of empirical rules. So the official name for the theory is called polyhedral skeletal electron pair theory. They're very simply these days called Wade's rules. So we'll look at how we can use those. There are a number of steps in Wade's rules that can be used to predict the structure of a borane cluster. So let's start simple. The question here is in bold, and it asks you to rationalize why B6H62- adopts an octahedral cage. So what we do is we invoke the steps in Wade's rules to rationalize and justify why that molecule adopts an octahedral cage. So the very first step is to determine the number of BH units. We assume that each boron atom carries a terminal hydrogen atom, and we know that each BH unit provides 2 electrons for cage bonding. So look in the pink box on the right there are 6 BH units in B6H62-. So that's step number 1 done. Step number 2, we need to count any additional hydrogen atoms, knowing that each one of those provides an additional electron for cage bonding. And in this particular example, there are no additional hydrogen atoms. Step number 3 then involves the addition or the summation of electrons that are available for cluster fragments, and we need to take account of any additional charge in the cluster. So here you can see that in this one, for example, there's a 2- charge, so we need to take that into account. And we determine the number of electron pairs. So here we know that we've got 6 BH units. Each one of those BH units provides 2 electrons for cluster bonding, so 6 times 2. We add an additional 2 to take account of the charge on the molecule, 2-. So that gives us a total of 14 electrons that are available for cluster bonding and 7 electron pairs. Step number 4 then, we take the number of electron pairs as equal to n plus 1, where n is the number of vertices in the parent deltahedron. So this allows us to determine the parent deltahedron. So we know that we've got 7 electron pairs, and the number of electron pairs is equal to n plus 1. So we know that there are 6 vertices in the parent deltahedron. If there are 6 vertices in the parent deltahedron, we know that the parent deltahedron is an octahedron. So you can go back to the slide a few slides ago where you look at all of those parent deltahedrons. What we then do is distribute the BH units over that parent deltahedron, and we know that each one of those BH units will occupy 1 vertex in the parent octahedron in this case. So look at the pink box on the right. 6 of those BH units occupy all vertices in the octahedron. And then the final step is that the number of vertices that are left vacant will determine the class of the cluster. So this allows us to determine the cluster class. You'll remember that if all of those vertices are occupied by a BH unit, then it's a closo structure. So there are no vertices left vacant here, and the cluster class is a closo structure. Okay, so let's have a look at another example. Here we're asked to suggest a likely structure for B5H8-. So again, we go back to the steps of Wade's rules. We determine the number of BH units. The number of BH units here is 5. In the second step, we count up any additional hydrogen atoms. Well, we know there are 3 additional hydrogen atoms here. We add up the number of electrons that are available for cluster fragments, taking into account any additional charge. So here I've got 5 times 2 for my BH units, plus 3 for my 3 additional hydrogen atoms, plus 1 to account for the charge on the molecule, which gives me 14 electrons, and 7 electron pairs. I know I've got 7 electron pairs, and I know that's equal to n plus 1, where n is my parent deltahedron. So I know that I've got 6 vertices in my parent deltahedron, and again, my parent deltahedron is therefore an octahedron. I then distribute those BH units about my octahedron, and I've got 5 BH units here, which I know will occupy 5 vertices of my parent octahedron. And then in step 6, I've got to determine whether or not I've got any vertices that are left vacant from my parent deltahedron. And of course, here I've got 1 vertex left, 1 vertice left vacant. So this is derived from an octahedron with 1 vertex vacant. And if I've got 1 vertex vacant, then I know that I've got a nido class borane. So this is nido B5H8-. Now, we've determined the class, but we haven't suggested a likely structure. So how do we go about suggesting a likely structure for the borane? Well, we know that this is a nidostructure which has been derived from an octahedral cage. So the first thing we've got to do is remove a vertex from that parent octahedron to get that square pyramidal structure that you see there. And we can think about suggesting a likely structure. So with the caveat that if one of those vertices is not equivalent, then the first to be left vacant tends to be one of a high connectivity or a cap in the structure. So you see the first one that we removed there is one of the capped structures, the point, if you like, of the octahedron. So if I distribute my BH units about my nidostructure, about my square pyramid, I've now got 3 extra hydrogen atoms, and I can form BHB bridges along 3 of the 4 edges of that square pyramidal structure. And again, there's a note here to say that if you've got additional hydrogen atoms, you tend to place them in bridging sites along the BB edges of an open face of the cluster, or you stick them in extra terminal sites. So that's how we might go about suggesting a likely structure based on the class. Now, the type of the types of reactions that these borane clusters undergo depends on the class and the size of the cage. And again, what I don't expect you to do here, this isn't organic chemistry, I'm not going to ask you to remember all of these reactions. What I want you to be able to do is predict the class of the borane in question and to suggest a likely structure for the borane. And there's loads of examples at the end that you can work through. But I think it's important that you have an overview of the kinds of chemistry that these borane clusters can undergo. So these, the first borane cluster to be synthesized was B6H62-, and the development of its chemistry was quite slow, but we can now make more of it. We've got improved synthetic routes, and we can quite easily access this B6H62-, and it will react with various things. You can yield cesium-based borane clusters by a reaction with cesium chloride. You can protonate those cesium structures. You can add hydrogens to various faces of a borane cluster, and you can perform proton and boron NMR and have a look at where those hydrogens sit. They're quite easy to chlorinate, brominate, or iodinate if you mix them with a halide in quite strongly basic solutions. The problem is you get quite a mixture of products. So if you take B6H62- and you mix it with the halide, either Cl2, Br2, or I2 in a strongly basic solution, you get a very mixed product. So there'll be a range of structures, each with a differing number of the halide on the molecule. So you can see the general formula there is B6H6-N XN2-. You can achieve monofluorination, so you can just get one fluoride molecule, one fluoride atom on the borane cage if you use xenon difluoride. But the problem is whilst it's monofluorinated, you still get a mixture of products where the fluorine either sits as a terminal fluorine atom or bridges the face of one of those vertexes. You can get quite a pure product whereby the fluorine sits on a terminal site on the cage, and you get a capped proton if you use quite specialist fluorinating agents, and the reaction conditions are quite complicated. But it's possible to halogenate them. It's just very complicated by a mixture of products. You can generate these very interesting conjuncto clusters where you have two clusters bonded together via shared boron-boron bond if you treat them with dibenzoyl peroxide. And there are a range of reactions that you can perform with the nidoborane B5H9 and the arachnoborane B4H10. You can get to a range of different products. Again, I do not expect you to remember these at all. It's just to give you an appreciation of the kind of rich chemistry that has developed, over the last 20 or 30 years in the field of borane chemistry. Now, importantly, you can mix the nidoborane B5H9 and the arachnoborane B4H10 with ethyne, and you generate an entirely new family of cluster compounds, and these are called the carboboranes. And structurally, these carboboranes resemble boranes, and you can rationalize their structures by using Wade's rules. It's just that the rules are slightly different. The only difference is that one of those CH units provides one more electron for bonding than a BH3 unit. So I show you a question here. Rationalize why the cage structure of C2B4H6 is an octahedron. So here there are 4 BH units and 2 CH units with no additional hydrogen atoms. We know that each BH unit provides 2 valence electrons, and we know that within Wade's rules each CH unit provides 3 electrons. So we can calculate the total number of cage bonding electrons available. There are 14 electrons, so 7 pairs, and we know that will lead to an octahedral parent cage, whereby each of those vertices is covered either by a CH unit or a BH unit. Now, just a bit of interesting chemistry, and people are constantly trying to push the frontiers of borane synthesis. You'll note on the slide where I showed you all of those parent deltahedra that essentially Wade's rules only go so far as a 12 vertex icosahedron. And that's because nobody's managed to synthesize anything whereby there are more than 12 vertices. That's not the case for carboboranes, and in 2003 a group managed to synthesize a 13 vortex closo carboborane, and it was prepared from a 12 vertex cage via a reduction, which opened the cage up and was then treated with an alkyl boron chloride molecule, which inserted another BH unit into the cage. And you can read the paper for the synthesis of that. I give you the reference there. Now, again, this is quite a complicated synthetic route, whereby they have to tether the 2 carbon atoms together so that the cluster doesn't rearrange or degrade. They're not very stable compounds, and that tether is an organic fragment that's added to the structure to stop it rearranging. And interestingly, the 13 vortex closer carboborane here adopts a polyhedron and not a deltahedron. And I mean, this kind of flies in the face of Wade's rules. So essentially, we're saying that Wade's rules break down somewhat when you have anything more than 12 vertices. And similarly, in 2005, a group prepared a 14 vertex carboborane. You can see the structure of that there. You can read the paper for its synthesis there. It's a very odd structured compound. So I guess the next question is, are we going to see a 15 or 16 vertex carboborane, or are we ever going to see a 13 vertex borane? Okay, I will leave it there. I've given you a number of questions that relate to practicing Wade's rules, and I would encourage you to practice these as much as you possibly can. The only way to get good at using Wade's rules and predicting the structure of these things is to practice them. So what I will do is maybe I'll go through the answers to some of these in one of our tutorials. Thank you very much.